In the previous video we estimated an exponential model for the number of COVID cases. And although we did pretty well for the first attempt, the problem with an exponential model is that it suggests that the number of cases can keep on rising, basically unboundedly. Yeah, so given the fact that the Dutch population is about 17 million people, obviously we cannot have more than 17 million cases. So another model to try to understand the number of cases is a logistic model, and it takes this form that you can see over here. So it's a constant c divided by 1 plus a times e to the power minus bt. So the thing to observe is that when t goes to infinity, this term basically goes to 0 for b positive, which means that at some point the number of cases y will plateau at this number c. Yeah, so we cannot get above the number c in terms of the number of cases. Yeah, so in terms of modeling an epidemic, that might actually be a good idea, because we know that the number of cases cannot go beyond the population size. Another thing to observe is that when t is equal to 0, so at the start of the modeling window, y0 is going to be equal to c divided by 1 plus a. Yeah, so that's what you can see over here. So although a is perhaps a hard parameter to find a prior for, we can actually rewrite this equation saying that a is equal to c divided by y0 minus 1. And this might be easier to find a prior for. Yeah, so I know there is this plateau c, so I can have an attempt at trying to understand what that could be, and there is this number of cases at the start, y0, and I can find a prior for that. And then when I have these two priors, I can actually get my prior for a. And I'm going to show you how you can actually do this in pymc3. So the model now takes the following form. So again, we have with PM model S, and I call this model the logistic model. So I'm defining my priors. So for y0, so the number of cases that we have at the start, let's say that could be 4,000, and then the standard deviation on that is 1,000. This is actually rather low, but as you will see, once we confront this with the data, this is actually corrected with a factor and number of times, about 10 times as big as what we specify here. Yeah, so the idea is that if you have enough data, the priors that you specify here are actually not that important. So here we choose it rather low, and it turns out to be a lot bigger than this. But the normal distribution for the prior actually allows for that to happen. So for B, which is basically sort of the growth rate in the number of cases, we specify again 0.1 and 0.1, so B can be negative in principle. C, which is this plateau that we're going to, of course, that cannot be negative, so let's specify it here as a uniform distribution. And let's say that the lower bound of this uniform distribution is 1,000, and the upper bound is about 10 million. Yeah, so the Dutch population is 17 million. I'm not an expert on epidemics. I'm not sure whether we should expect all 17 million people to get corona at some point. So you can experiment with this. I put the plateau here at 10 million. Yeah, so the idea of this model is that we can never have more than 10 million COVID cases. Now, of course, an important parameter in the model is a, but it's hard to find the prior for a. But now what we can say is that a is basically c divided by y0 minus 1. Yeah, so we have this term here, pm deterministic, which is similar to pm normal, except that it says that there is no added uncertainty here. Yeah, so the pm normal basically says that around the mu is 4,000 and the sigma of 1,000, I draw elements to get y0. That's not the case here. I'm not drawing elements. I'm simply saying that a, the parameter a, is equal to c divided by y0, and c and y0 themselves are random variables. Yeah, so A will be a random variable as well, but all the properties of A will be inherited from the properties of C and Y0. And this expression here, C divided by Y0 minus 1. Yeah, so I'm simply using the equation that we have here for A. There's no need to specify more uncertainty than this, so I don't need to specify distribution here, because this is basically a deterministic relationship between the parameter A and the parameters C and Y0. By specifying it like this, A will actually be generated both in my prior predictive but also in the posterior distributions. Yeah, so in principle, like if that's actually not needed, if I actually do not need to know the parameter A later on, I could simply have written A is equal to C divided by Y0 minus 1. That would have worked as well, but then I don't get posterior distributions on A, which I want in this case, so that's why I use this expression with deterministic. Then I specify the equation for Y, so this is basically the equation that we have over here. So we say Y is C divided by 1 plus A times, and I'm using the exponential function here again from pymc3 itself, minus B times T. I specify the noise term, EPS, and then I say that log cases is the log normal distribution. Again, repeat the name of the variable, in this case log cases. It's going to be the log of Y, because Y is the number of cases, but I'm modeling the log of the number of cases here, so I'm using this log term again from the pymc3 library. And observed is log cases. And first I'm going to sample from the prior predictive, and I'm going to have 50 samples. So I can run this code to see whether I didn't make any mistakes. Apparently not. So now we can sample from our prior predictive, and in this case I have a few more variables, so I can now say for A, B, and C in, and I'm using zip again. So I'm going to get prior predictive 2, yeah, because that's what we called it here. First for the parameter A, prior predictive 2 for the parameter B, and prior predictive 2 for the parameter C. Then what we find is that Y is equal to C divided by 1 plus A times, here I can use numpy because I'm not in an pymc3 block, minus B times T. Oops, not sure what happens here. Y is C divided by 1 plus A times the exponential, that looks okay. Then we say PLT plot T and Y. I'll fix the color at black. Transparency alpha is equal to 0.4. And then finally, let's say PLT Y lim, because some of these draws can be pretty big, so let's not go beyond 500,000. So let's see what we get when we run this. So here we have our draws from the prior predictive. So you can see that we have a number of draws where indeed we find this plateau. Of course, we know in our data, we don't plateau within this time frame. So in the posterior, these particular draws from the posterior distribution are not very likely to actually get much mass. Again, I'm sort of, in the right ballpark, sort of around 300,000. I can cover most of them. Some of my draws are a bit below that, so there are very low ones here, there are very high ones here. But in principle, I'm covering the space of what could happen for this number of cases, simply based on the prior distribution. So from here I leave it to you, using what we did in the previous video to actually find the trace when we confront this prior distribution with our data. So find the posterior predictive, plot the trace, plot the summary of the trace, look at the values for R hat, and then plot posterior predictive, so have the real data on the number of cases combined with the 95 prediction interval for this model. But these are basically the same steps that we did before, so I'll leave it to you to actually complete the analysis for the logistic model that we have here.